Try it quickly. These will not take long. All right, top one. Who can raise their hand that I haven't heard from today? Give me an answer. Elizabeth, you got this?
6.8.
How'd you get that, Elizabeth?
Because they're equal.
Yeah, regular theorem or converse, are you not sure?
Regular.
Yeah, let's go through the regular one more time. If a point lies on the perpendicular bisector. Okay, so that's our hypothesis. Does S lie on the perpendicular bisector? Yeah. S is on that perpendicular bisector. Conclusion? S is the same distance to P as it is to R. So she said RS must be 6.8 as well. By the regular perpendicular bisector theorem. Are we good with that? Yes? Next one. McKenna.
19.
I hear 19. You guys agree? Let's look closely because they didn't ask for EF. They asked for EG. Oh, look. H is equidistant to the endpoints. H must be on the perpendicular bisector. And therefore, that whole segment is double 9.5. Would you say 19?
Yeah, I think so.
I forgot if you said 18 or 19. Double 9.5, 19. Regular theorem, converse. Who votes regular? Who votes converse? I vote converse. All right. Ooh. Got some variables in it now. Jackson.
You want the answer?
Oh, let's go to process first. D is on the... D is on the... What's this thing called again?
An angle bisector.
Not angle bisector, but the
segment bisector. Or the perpendicular bisector.
There you go. Therefore, D must be equidistant to the endpoints. So what did you do with those expressions?
Set them to each other.
Good.
Got 7 for X and plug it in and get 35.
And ask for AD. AD is 5 times 7, which is 35. I like it. You guys good with that? What about angle bisectors? You have to train your eyes to look at a different part of the picture, and I will be honest with you. Let's go back for one slide because I want to point out something that is not obvious to all, okay? Do you agree the end result of this is an isosceles triangle? Do you see it? Congruent, right? Isosceles triangle. In a triangle, does the perpendicular bisector of a side always have to go through the opposite vertex? Ready? Let's draw the perpendicular bisector of this side. Do you agree the midpoint's about in here? If I draw the perpendicular bisector, wouldn't it be right there? Is this point on the perpendicular bisector? No. So this is not an isosceles triangle. That point is not, it's not equidistant to these vertices. It's not because it's not on the perpendicular bisector. You good, Ryan? In a minute? You good?
Yeah, I'm good.
You good? Oh, you got water.
Yeah, talking about the water.
All right, you got this. If you need CPR, I am trained. I don't have my card with me though. You can go and get it first if you need me to.
I'm good.
Okay. All right. Do you agree? The green dot is not on the perpendicular bisector. So it's not equidistant to the endpoints. So these cases we've been doing, there were special cases where this vertex was on the perpendicular bisector, and we talked about the result of the theorem. Okay? And in all those situations, those were isosceles. Now we're looking at these situations, and we say, here's an angle. Everybody see this black angle, BAC? What happens if you bisect an angle? You get two congruent angles. Cut or bisect cake. Two equal pieces of cake. All right, bisect an angle. Two equal angles. So the result of an angle bisector is two congruent angles. Right there. Right there. So now there is an angle bisector theorem that talks about what if a vertex is on an angle bisector? Isn't AD called the angle bisector? Isn't that the one doing the cutting? Right? AD is the angle bisector, and point D is on the angle bisector. There are some interesting results from this. We get two theorems, the angle bisector theorem and the converse of the angle bisector theorem. If a point lies on the angle bisector, what point are we talking about here? What point lies on the angle bisector? D, very good. D lies on the angle bisector. What's the name of the angle bisector? Sorry, I will unfreeze that screen. I forgot to unfreeze it. What's the name of the angle bisector in this picture? Emma, what do you think? What would you name that angle bisector up there?
Angle BAC.
That's the angle that's being bisected. What's the name of the thing doing the cutting in half? Is it a line? Is it a ray? Is it a segment? AD. Good. Ray AD is the angle bisector. Conclusion? D is the same distance from the sides of the angle. So D to B and D to C are the same length. And the converse of that is also true. If D is the same length to the sides of the angle, it must be on the angle bisector. Now, I need to draw something in very important that you might not see drawn in sometimes. Watch up here real quick. What if I get rid of this stuff? Do you agree D is on the angle bisector? D is on the angle bisector. So it's the same distance. What it's trying to say, it's the same distance to these rays. But what are you talking about? Like, is it this distance? Is it that distance? Is it this distance? It's the shortest distance. Do you see what I'm talking about? If I want to walk if I'm on the angle bisector and I want to walk to this ray and I'm like tired, I don't want to walk far. The shortest distance, oh yeah, back in chapter 1, the shortest distance from a point to a line is the perpendicular segment from the point to the line. Do you agree? DB is the shortest distance. Everything else would be longer. Do you agree? So when it says it's the same distance, what distance is it talking about? The perpendicular distance from the point to the line. Okay? The converse is also true. We talked about that. Let's do a couple quick examples, and you'll be on your way. Is there enough information to conclude that QS bisects angle PQR? Now, I guess I said it correctly, but I want to also be clear. Watch up here. Do you agree this is the shortest distance? But could I have told you another segment, like D is the same distance at other points on the lines or the rays? Well, let's read the theorem. If a point lies on the bisector of an angle, is D still on the bisector of an angle? Yes. Then it is equidistant from the two sides. Okay. Well, what if D is equidistant to the two sides somewhere else? Is D still on the angle bisector? Yeah. So, do you agree these are not the perpendicular segments that connect those? But there's still a pair of congruent segments to the sides of the angle, right? So S must be on the, what's the conclusion? S must be on the perpendicular bisector, angle bisector. S must be on the angle bisector. S is equidistant to the sides of the angle. So S must be on the angle bisector. All right. 2 examples. Looking at the picture, is J equidistant to the sides of this black angle? Yes, 7, 7. Therefore, JF is the angle bisector. This angle has to be 42. Now let's see what they're asking us. They're asking us for GFJ. Oh, that's the one we just found. GFJ is 42 degrees. Converse of the angle bisector theorem. Converse. We didn't know it was an angle bisector. We concluded that it was an angle bisector. Next one. Oh, look. This angle has been cut in half. Therefore, S is on the angle bisector. Therefore, S is equidistant to the sides. So we're going to set 5x equal to 6x minus 5. Subtract 6x, we get negative x equals negative 5. X equals 5. Our S is 6 times 5 minus 5, which is 25 units. 25 units. Does that make sense? How to solve those? So you have to kind of train your eyes, look at the picture and decide, do I have enough information to use one of those theorems? And then what's the conclusion of it? That kind of helps you set it up. We're sticking with the soccer theme today. Are you ready? You got a player, one-on-one situation with the goalie. Okay? One-on-one. Where should the goalie stand? On the angle bisector. Between, because if they're out here, Point B is out here. Ready? Goal. Goal. The goalie would move over to there, wouldn't they? To be on the angle bisector. You ever play tennis? Returning the serve. Here's your box. There's the server. You want to be on the angle bisector of the box. Basketball, you want to defend. Okay, you got the backboard, the rim. You want to be on the angle bisector in your defense, unless you're playing like zone or something. Homework. If you looked this morning, not that you would, I trimmed it down a bit. It's this assignment.
So if we're at example,
If they're on the perpendicular bisector, then they're always going to stand on this line. But if the person shooting the ball is over here, you don't want to be out here.
So you're saying if that top point right up there moves, it's always going to move.
If it's an angle bisector, the goalie should move. They would never move.
Like I have 5 seconds. If this is not how you draw it. Because you're saying this is the goal. This is the goal box. And we got our second box. It's outside of the goal box. Yeah, here. It's not. Yeah. It's outside of the goal box.
The penalty kick is outside the goal box.
Yes. This. Because we got the goal here.
Are you talking about the little box right here?
Yeah, you're saying this whole thing is goal. Goal box surrounds the entire goal.
This is the goal.
Oh, no.
This is the goal right here. This is the out of bounds.
So the rest of it.
This is the goal box. This is the PK.
Oh, right.